Here we are at section B finally. We're looking forward to getting there. Let me get my pen ready. Okay, we've done this. Now we're getting into sum and difference identities. We're going to spend quite a bit of time today actually deriving our first one. After we get the first one, the rest don't take so long. Hang up and derive. Cell phone use at the math board. That could be even worse than cell phone use behind the wheel. Cosine of a difference. Now, before we get into this, I have to work on this, the law of additivity. We'd like to believe that this is true, that the value of function with inputs of u plus v is going to be the sum of f at u and f at v. Unfortunately, that's not usually true. Very few functions follow that rule. The Hall of Fame for algebraic blunders, this would probably be right up there, these two. And they both are making the mistake of thinking that u plus v, and here what is the function? It's squaring, is going to be the same thing as squaring this plus squaring that. Well, just to make sure that we don't believe that, let's try one. So if u were equal to 1 and v were equal to 2, then we'd have, let's see, 3 squared, right? And we'd be wondering if it's equal to 1 squared plus 2 squared. Clearly it's not. So that's one of them. Now let me find something that's using perfect squares for my second run here. Instead of, let's see, I'll try to get some numbers that are good. Say u is 9 and v is 16. Right? So I'm going to take the square root of u plus v, which would give me what? 25. Square root of 25. Is that equal to the square root of 9 plus the square root of 16? Is 5 equal to 3 plus 4? No. Okay, so I think that's all it takes for you to recognize that having the inputs sum together does not equal those two functions sum together. So that makes a difference here because we're going to be doing, here we're going to do sine, and here we're going to do cosine. Let's find the sine of u and the sine of v. Well, the sine of pi is 0, right? The sine of pi over 2 is 1. The sine of pi plus pi over 2, that would be going 3/4 of the way around a unit circle, right? And what have I got here for my sine? -1. Does -1 equal 0 plus 1? No, it doesn't. Well, let's try this for cosine, and we'll think of u as being 0. Let me see, cosine of 0 degrees, well, or 0 radians, we're talking radians here, is 1. And if v is 2 pi, the sine, or the cosine of 2 pi, I'm going all the way over to here again, that's also 1. The cosine of 0 plus 2 pi would be 1. So does cosine of the sum of these two angles equal the cosine of the first angle plus the cosine of the second angle? No. I just want you to be totally convinced that the law of additivity doesn't play here. And we could do the same thing, I'm not going to, for tangent. We can't do it with any of these trig functions. I'm sure you're convinced by now. I'm going to show you a proof of what, or a derivation of formulas that we can use for u plus v or u minus v, plus or minus. So we can take sums or differences of angles. We can't just add or subtract the sine functions from each other, but there is a way to do it. And let's derive that right now. This is probably, this is nothing I expect you to remember. I just want to so totally convince you that you will always use the right formula here. We've got some angles. We've got angle u. We can see, gee, what angle is that? Maybe it doesn't matter. 180 and another 45, so it's 225. We've got angle v, which looks like it's 150, right? And then we've got the difference between them. So that's 15, 30, 45, 60, 75 degrees. So we have a theta, which is the difference between them. Angles u and v are in standard position. True, right? They've got positive x as their starting ray. The point coordinates a and b represent a point on the terminal side. The measure of angle theta is the difference between these two. Okay, so we've got our setup here. The unit circle that we're looking at here is the one we just were looking at, and what I have done is I put in some point coordinates. Because this is a unit circle, I can say that my x is cosine of angle v, my y is the sine of angle v. And I can do the same thing for this larger angle u, cosine and sine. Now, this angle right here, which has these terminal points on it, I'm going to put that into standard position. So it's still theta, or we can see here 75 degrees. And I can't use the same points, obviously. So I'm going to name them C and D. D, I know, because it's a quadrantal, is 1, 0. And this one, I'm going to ignore what the actual angle is. I'm just going to say it's cosine theta sine theta. The chords, AB, right here, AB, and CD, right here, are the same length. So I could use a distance formula and say the distance of this and the distance of this are identical, which is what we're going to do right now. The what is that distance formula again? Let's go back here. It's you choose one of your points to be your second point and the other point to be your first. Take the difference between the coordinates and that's a length squared of a right triangle, right? And then length squared. So we'll do that here for AB, that was our original one, and then for CD. Now, let's simplify this. This is my x value for point, oops, I better make sure I get it straight. That's my x value for point B. All right. My x value for point B minus my x value for point A, my y value for point B minus my x value for point A, and then I do the same thing here. So I want to simplify. I'm going to use algebra and fundamental identities. First of all, I'm going to square both sides. Whenever you have an equation, as long as you do the same thing to both sides, you're okay. So I'll end up with cosine squared v minus 2 cosine v cosine u plus cosine u squared. So that's just this one. I'll swap pen colors to try and help you follow, make it easier for you to follow me. Then I'm going to do this next one, plus, and this will be sine squared v minus 2 sine v sine u plus sine squared u. And that's just one side of the equation, right? And we say that is equal to, I wonder if I have enough pen colors. Now the other side of the equation will be cosine squared theta minus 2 cosine theta plus 1. So that's this one. And I have one more pen color, just right, huh? This one, plus sine squared theta. Oh, that's all it's going to be. Oh, thank goodness for that. Wow. All right. So now I'm going to look for simplification opportunities. Change my pen again. I'll go back to green. I don't see any, is there any simplification opportunity here? Oh, yes. Cosine, we're going to use the Pythagorean identity. Cosine v plus sine v, what is that equal to? That's equal to 1, right? Okay, so take care of that. Cosine squared u and sine squared u, again, equal to 1, right? Hey, I'm liking this. So plus another 1. Then I've got, oh, this is a little trickier, minus 2 cosine v cosine u. So I've written that one in. And minus 2 sine v sine u. So I got one side of the equation done. And over here, what have I got? Well, again, I've got the Pythagorean identity going to help me out. I'm going to have 1, because sine squared theta plus cosine squared theta is equal to 1. I have a 1 here. I might as well put that in. Plus 1. And then I've got a negative, whoop, a negative 2 cosine theta. Aha! So what can I do with this? Well, if I subtract 2 from both sides, those will be gone. And then if I divide everything that's left by -2, remember you do it to all terms, I end up with cosine V cosine U plus sine V sine U equals cosine theta. All right, so this is what we ended up with when we did the algebra. And what fundamental identity? We only used one, the Pythagorean. Now I want to express this solely in terms of angles U and V. So I want to get rid of theta. Well, what does theta represent? It's the difference between U and V. Specifically, it's U minus V. That's what theta is. So we can do it. So there's the cosine of difference. U minus V, and those could be any two angles, right? We can figure out what that is by multiplying together the cosines of both angles, adding the product of the sines of both angles. So to find the difference, you're going to add those two products. Now, you're probably wondering, why do we even bother with all of this? Well, I'm going to be asking you to do a lot of work without using your calculator. So find the exact value of the cosine of 15 degrees. But if you look on your unit circle, now remember, you don't have your calculator. You look on your unit circle, 15, we can actually find 15, but when you look out here at point coordinates, there's nothing there. So let me show you how handy this is. We do have something there for 45 degrees, don't we? There's a point coordinates for that. We have point coordinates for 30. What's the difference between them? 15. So clever, right? So no calculator, just have your unit circle, and if I ask you to find the cosine of 15 degrees, you say, no problem. You take the point coordinate, the x coordinate actually, for 45 degrees right here, times the x coordinate for 30 degrees, and then you go ahead and do the same thing for your y coordinates. Now it's just a matter of doing the algebra. Well, you get a very messy answer, but this is the answer I want. Don't you dare give me a decimal answer here. No decimal. Because if you use decimal, what does that tell me? There's no way you could get to decimal without using your calculator. Well, no way for the average bear to do it anyway. Cosine of a sum. So we know cosine of a difference. That one we derived. We can derive the formula for the cosine of a sum from this, and I'll show you how. We're going to take the cosine of alpha plus beta. That's what we're starting with, cosine of sum, and we're going to set it up. This is so tricky. We set it up with a negative angle. Sure, I can convert anything into a difference, right? Instead of adding a positive beta, I'm going to subtract a negative beta. So it is exactly the same value, but it's expressed so that I can now use cosine of a difference. And when I do, you can see what happens. I end up with cosine of negative beta. So that's what's, let me get my pen. So right here, every place we have a beta, we have to put in what we substituted, the negative beta. Now we know the negative angle identities. Cosine is an even function, so that one translates just to cosine beta. Sine is odd, so that one translates to a negative. So the cosine of a sum, it looks a lot like the cosine of a difference, doesn't it? The only thing you notice is the sign. And I'm going to erase this, so I'll make this really clear here. Okay, try red. So when we're finding the difference, we add the products. When we're finding the sum, we subtract the products. And notice we have the cosines as our first product and the sines as our second product. Co-function identities. We've looked at these before. This is just saying that the complement of angle theta, its sine is equal to the cosine of theta. We did this way back in the beginning. So these are the co-function identities. But remember, we called these co-functions sine and cosine, tan and cotan, secant and cosecant. So there's another 6 identities for you. Wow. What have we got so far? We've got the fundamental identities, of which there are 11. Then we had the negative angle identities, and there are 6 of those, and then 6 of these. So they're adding up. Confirming co-function identities. All right. We can now prove, at least in a different way, the complementary angle of theta. The cosine of the complementary is going to equal the sine of that angle. And we can prove it here using the cosine of a difference, because what is this? This is the cosine of the difference between 90 degrees and some angle. We don't know what that angle is. That's not going to bother us here. Okay, we don't know what this angle is. But we know all the other angles, don't we? So for the others, we can put in a value. What is the cosine of pi over 2? Cosine of 90 degrees is 0. So that's 0. Cosine of theta we don't know, but the sine of 90 degrees, we certainly know that. That's 1. 0 times this will cause that to disappear, won't it? You end up with sine theta. So did we prove it? Yes, we did. Let's move on to sine of sum. Derive the formula for the sine of sum using the cofunction identities. So we're not deriving all of them. I'm not taking the time to do it. You can work through it yourself if you would like to. We now have the sine of a difference and the sine of a sum. the thing to notice here is that with sine, when you're summing the angles, you sum the products. The other thing to notice is the products have changed a lot. Now your product is the sine of your first angle and the cosine of your second. And then for your second term, the cosine of your first angle and the sine of the second. With difference, you've got the same products, but you're subtracting them. The sign does not switch. So with these new identities, you can answer this question without using your calculator. 105 degrees. Whew. I'm asking you to do that without your calculator, and obviously you don't have 105 degrees on your unit circle. However, you do have 45 degrees, and you do have 60 degrees. So you use those, and again, you end up with an exact answer, and this is what you're going to give to me, an exact answer. Tangent of a difference. Let me show you those. We can use identities and algebra to derive these. I don't expect you to memorize these. I will let you use an identity cheat sheet to help you out with these when you need to use them. So there's the difference, there's the sum. So when you're asked to find the value for pi over 12 and you look on a unit circle, there's nothing there for 30 degrees or pi over 12. However, you could do it this way. There is something there for pi over 3 or 60 degrees. There is something there for pi over 4 or 45 degrees. So you can use those two values to get yourself pi over 12, just using the tangent of difference. And again, you're going to give me an exact answer, no decimals. Sum and difference formulas. Let me see what else we've got ahead of us here. We're going to do this one, and then the next two I'm going to let you work on in class. Okay, find the exact value of the sine of 75 degrees. We don't have 75 degrees on our unit circle, but what do we have? We have 45 degrees. So we can do the sine of 45 plus 30 degrees. Whoa! You have it for reference here. And I'll make it a little bit smaller so it doesn't take up so much room. Now you're going to use your unit circle as reference here. And you're going to say the sine of alpha. In this case, what is alpha? The sine of 45 degrees times the cosine of beta times the cosine of 30 degrees. We're summing and we're working with the sine, so we're going to add the products. And now we're going to do the cosine of 45 degrees and the sine of 30 degrees. Okay, so we know what these are. We can look on our unit circle and we see them. what is the sine of 45 degrees? It's 1 over the square root of 2. The cosine of 30 degrees that's the square root of 3 over 2 plus the cosine of 45 degrees and the sine of 30 degrees. So I end up with, let's find these two products, the square root of 3 over square root of 2 times 2 plus 1 over the square root of 2 times 2. So I have the square root of 3 plus 1 divided by square root of 2 times 2. So that's a pretty good answer, but if I wanted to rationalize the denominator here, I'd end up with the square root of 6 plus the square root of 2 over 4. What did I do? I just multiplied both the numerator and the denominator by the square root of 2. Okay? Right. Move this right over here. And we'll work on this one, the exact value of cosine of 75 degrees. Here again, I'm going to use a sum. I'm going to say cosine of 30 degrees plus 45 degrees equals okay, here we are with these here for our reference. When I'm doing cosine and I'm looking at the sum of angles, I'm actually going to take the difference of the two products. And the products, of course, are both of the cosines followed by both of the sines. So I've got cosine 30 degrees times cosine 45 degrees. Oops, nope. It's going to be minus. And then I'm going to say sine 30 degrees sine 45 degrees. And again, let's look at our little, I don't have my unit circle in front of me, so I usually just do a little drawing. The cosine of 30 degrees is going to be the square root of 3 over 2. The cosine of 45 degrees is going to be 1 over square root of 2. And I'm going to subtract the sine of 30 degrees, which is 1 over 2, times the sine of 45 degrees, 1 over the square root of 2. So I end up with the square root of 3 minus 1 over 2 square roots of 2, or perhaps I want to write it as the square root of 6 minus the square root of 2. See, I'm multiplying my numerator by the square root of 2. There. Okay, I rearranged the sheet a little bit and brought over our tangent sum, tangent difference to do this next one. Find the exact value. Of course, exact tells you that you're going to have to do something other than using your calculator, aren't you? Find the exact value of tangent of 75 degrees. So I could find it with a sum, right? Which would be the tangent of, we're getting used to this now, 30 degrees plus 45 degrees. Or I could find it as the tangent of, how am I going to get to 75 degrees? Could I use a difference? And if I do, what's it going to be the difference of? Okay, so let me think. What do I've got? I've got 90, but it's not, I can't just subtract 75. What if I used 120? I had 120 and I subtracted 45. What would I have left? $75. So that would work. Am I right about that? So I could say 120 degrees minus 45 degrees. Ooh, nice. So we can go either way with this, and I just would use these formulas. I'm not going to spend the time with it right now. And we'll leave this one for you to do in class. Plus, you're going to have plenty to do in class. I'm going to have you work this example and this example as work that you're going to do back in the classroom. So we'll finish up with example 4, 5, and 6 in the classroom.